Dr. Charlie Smith, and this is a tutorial on how to calculate the range, variance, and standard deviation for raw sample data. The range, the variance, and the standard deviation, these are all measurements of the spread of the data. If the data were plotted on a number line, how would they be scattered out? Would they be far apart, or would they be clustered close together? These are all measurements of the spread or the scattering of the data. The easiest of these to calculate is the range. And the range is defined simply to be the largest x value minus the smallest x value. Now, here we have our table of x values from the previous tutorial. They are arranged in numerical order from lowest to highest. So we see that the largest x value is 30 minus the smallest x value is 12. So 30 minus 12, that's 18. So the range is 18. Right. Now, there are two ways to calculate the variance. And I'm going to show both ways and let you decide which formula you like best, because both formulas that I'm going to show you will give you the exact same answer, because the two formulas are actually identical, even though they don't look the same, but they are identical. This is the formula that defines what the variance is. The symbol for the variance is s squared. I know that seems a little strange, but the symbol for the variance is s squared. And it's defined to be summation of x minus x bar quantity squared, all divided by n minus 1. Note that this formula depends on a prior calculation of x bar. In other words, the mean has to be calculated in advance before this formula can be used. This depends upon the prior determination of what the mean is. Otherwise, you can't even start here. Well, in the previous tutorial, we calculated the mean, and we found the mean x bar to be 18.75. So this is really 18.75 for our purposes. So if we look over here, I have another column set up ready to go. I want a column for x minus x bar squared, but we know our x bar is 18.75. So this is really taking x, subtracting 18.75, and then squaring the whole thing. So the first calculation here is going to be for the x value of 12, to take 12, subtract the mean, which is 18.75, and square it. And when you do that on your calculator, you will come up with 45.5625. And I'm keeping all the digits. Rounding can be dangerous. Round-off error can snowball. So we want our answer to be as accurate as possible. For the next calculation, 14, I put 14 in place of x. And so I take 14, subtract the mean, which is 18.75, and I square that. And so the next number in the list is going to be 22.5625. The next one obviously is going to be the same, 22.5625. And the next one also 22.5625. And now proceeding in the same manner, using the same method, we get the last four numbers to be 1.5625, and the next entry is 10.5625, after which when I put in 24, I get 27.5625. And when x is 30, we get 126.565. Now, if you think this is rather tedious and cumbersome, you're right. This is rather tedious and cumbersome. This formula is only easy to use if x bar, the mean, happens to be an integer, a whole number. Otherwise, it is somewhat tedious to use. When we add all the numbers in this column, we get, surprisingly, 279.5 exactly. 279.5. So now I'm ready for this formula. We know that n is equal to 8, that's our sample size. And we know that the summation of the quantities x minus x bar squared, we know that that summation is equal to 279.5. So, plugging those numbers in, this number is the numerator of our fraction. So on top here, 279.5 divided by, in the denominator of the fraction, n minus 1, that's going to be 7. And dividing, and I rounded these to the nearest hundredth place, to the nearest two decimal places, I get a variance of 39.93. Now, for us, the variance is the first big leap on the way to the standard deviation, which is more important. It's a small step. After this giant leap to the variance, it's a very small step to the standard deviation, because the standard deviation is always defined to be the square root of the variance. And that's true no matter what type of data we're working with. The standard deviation is always equal to the square root of the variance. So our standard deviation for this data is going to be the square root of 39.93. And again, I rounded this to two decimal places. We get a standard deviation of 6.32. Now, that's quite a lot of work, and that's why this formula, while correct and will always get you the right answer, can be rather cumbersome and as I said, tedious to use. Now, through the magic of algebra, this formula can be manipulated and converted, and follow me over here, it can be converted into this formula, which we call a computational formula, because it's easier to use when actually calculating the variance. Excuse me. Now, this formula may look more difficult than the formula over there, but they're actually equal. They are identical. And it's easier, in practice, it's easier to work with this formula, and I will show you why. Again, we need two columns, but our columns are going to be one column for the x values and another column for x squared values. So now we're just simply going to do what the columns tell us to do, and we're going to square each value of x. That's all there is to it. 12 squared is 144. 14 squared is 196. And I have three of those, so 196, 196, 196. 20 squared, well, that's 400. Now I have to look at the paper. 22 squared is 484. I'm just squaring each x value. I get the numbers in the next column. The last two here are 576 and 900. Now I add up all the numbers in the x squared column, and I get 3,092. Now, in order to apply this formula, we need three things. We need the value of n. That's our sample size. We know n to be equal to 8. We need sigma x right here. Sigma x is the sum of the x values. We know that to be 150. Sigma x is 150. And we need sigma of x squared, the sum of the squares of the x values. And we know that value to be 3,092 right here. So summation of x squared is 3,092. And now using these three numbers, which were easily obtained, we plug them into the formula and we calculate. So n, 8, times sigma x squared, that's 3,092, minus sigma x, which is 150, squared, all divided by n, which is 8, times n minus 1, which is 7. Now, the number on top can be easily obtained on a calculator simply by entering the numbers and the operations in the order that they occur from left to right. So to get the number on top, you just enter 8 times 3,092, then hit minus, then enter 150, and then hit the automatic squaring button, and then hit equals. And that will give you, in one smooth motion, that will give you the number on top. So the number on top turns out to be 2,236. Divided by 56. And when we divide this out, and this is no surprise, we get the same variance as we did previously. It has to give us the same answer. And it does. It gives us an answer of 39.93. And the standard deviation, of course, if we take this route, we haven't calculated the standard deviation yet, if we use the other formula. So we still have to calculate the standard deviation. That's always equal to the square root of the variance. So again, the square root of 39.93, which is that 6.32. One thing of extreme importance here, when you calculate the variance by either formula, this is the variance, this number must be positive. If you get a negative number here for the variance, you have done something wrong. You made a mistake somewhere, so go back and recheck your work. The variance must be positive. In one extreme example, the variance could be 0, but you won't see that. For our purposes in this class, the variance has to be a positive number. That's extremely important. Was there anything else that I wanted to stress? No, the variance has to be positive. And so now you have two different ways of calculating the variance. I contend that this method is much easier to use and will serve you better in the long run. And so I thank you for watching this episode. Next time we'll be dealing with a different type of data, data that's organized and grouped into something called a frequency distribution. Thank you.